Hello, this is Miss Williams, and we are at Topic 6, Lesson 1. Today we are working on key features of exponential functions. You should have your new vocab sheet out ready because we have 5 words. Okay. Today we'll be focusing on recognizing the key features of exponential functions. So, how do graphs and equations communicate key features of exponential growth and decay? So we're going to jump right into it. We're going to talk about what is an exponential function. Okay, so an exponential function is one of your vocab words. It is in the form of a times b to the x. Okay, where a and b are constants, a is not 0, and b must be greater than 0 but not equal to 1. Okay, and so part of the biggest thing is that these are going to be 2 separate numbers, remembering that I cannot actually multiply a and b together without taking the exponent first. So let's kind of check out just a more basic function. We have f of x is equal to 2 raised to the x. In the end, we're going to find all these key features, but first let's build this graph a little bit. Now we probably can do this on our own. Okay, so I'm going to start with maybe -2, -1, 0, 1, 2. I might even go to 3. So if I took, let's talk about 0. Let's start here. Anything to the 0 power should be 1. 2 to the first is 2. 2 to the second is 4, 2 cubed is 8. Okay, now if I put in -1, remember exponents would make this flip, giving us 1/2. Okay, 2 to the -2 should be 1/4. Okay, now if you aren't sure on those or want a faster method, you can always go to y equals, and I'm going to type in 2 raised to the x, and I'm going to hit graph, and what I'm going to do is just go second table, and I can see those values there. Now these give you decimals, so but we know that this is 1/4 and 1/2. Okay, so let's draw a rough sketch. Okay, so we have -2, 1/4, -2, or -1.5, 0, 1, 1, 2, 2, 4, 3, 8. And it's going to look something like that. Okay, let's talk about our key features. Okay. Let's talk about our domain. Okay, what can we plug in for x? Is there any restrictions here? And that would be no. So we're going to say all reals. Or that could be -infinity to infinity. Our range, what's the lowest we can go? And we're approaching, right, even on my calculator I can see it probably a little bit better. We're going to approach 0. So y has to be greater than 0. It is not equal. It's not going to equal it. Okay. We got our intercept. So we have our y-intercept. That is the coordinate 0, 1. Okay. We do not have an x-intercept. Okay. We got asymptote. Okay, so this is where does the graph approach. And that would be 0. Now, this is going to be a line. And so we're going to say y equals 0, or in other words, that is the x-axis. Okay, and lastly, we have our end behavior. We worked on this a little bit earlier. Remember, it's always x goes to negative infinity and x goes to positive infinity. Then where does y go to? And then we're going to do the same. And so it's those two. Okay, so as x goes to negative infinity, so as we go to the left, where are we approaching? And that would be 0. As we go to the right, where is my graph going towards? Well, infinity. Okay, so those are the key features of our graph. Okay, so let's talk about this one. Okay, now I would say I can argue you can graph this on your calculator. Okay, but I want you to give me the table of values from the calculator so I can see an accurate graph. Okay, so go ahead, pause the video and do those two things for me. Graph it and find the points. Okay, and so we should have, I'm going to bring up my graph. I'm finding my values from the table. And we're going, -1 gave me 8, 0 gave me 4, 1 gave me 2, 2 gave me 1, 4 gave me, 3 gave me 1/2, 4 gave me 1/4. Now I got that right from my table, right? I graphed it. And so here's what our graph should look like roughly. Okay, so our domain still all reals. Our range is still y is greater than 0. We have our asymptote. What are we approaching? That is still y equals 0. And our end behavior, when x goes to negative infinity and x goes to positive infinity, what does y do? Y, as I'm going to the left for negative infinity, I'm actually going to positive infinity. And as I go to the right, I'm going to 0. Okay, so you should be able to graph it on your calculator, get the values. I want to see the values that you are graphing with, and then answer those questions. Okay, now let's talk about some transformations. Okay, so here's the graph, right? I want to know if this is my parent function right here. I don't know then how does this impact it. So I want you to think about, is this negative outside or inside the function, right, and go through our process. Is it true or opposite, x or y, those types of things. Okay, so if you remembered, you should say that this is outside the function, and the negative is talking about reflection, and this would be over the x-axis. Now, again, you can get your values from the table. So you should have graphed it and get your values. Okay. And there's our graph roughly. Again, we can have it in our on our calculator. So if we go through each of our pieces, right, we're going to compare just the asymptote and the intercepts to the function. So my asymptote of my original would have been, right, if I'm just reflecting this, this would be f of x of 3x. So this is considered the parent function. So the asymptote is the same, and it's still y equals 0. Now let's look at the x-intercept. So this x-intercept would have been at 0, -1. So our y-intercept is at 0, -1, and which is it's different from the parent function. Okay. Now let's bring in some end behavior here, even though it doesn't ask for it. So as x is going to -infinity, what is my blue graph going towards? And that should be 0. Even though we're on the bottom, it's still headed towards 0. Whereas my right, which is positive infinity, is actually heading towards -infinity. Okay. So we were reflected over the x-axis with a negative on the outside. Okay. Our transformations are still true, inside, outside, those types of things. Okay, so that's what we're going to work on kind of next. Right, so I want you to talk to your partner to tell me, where do you think this graph is going? Okay, so you should have thought that this is outside, which is y, which is true, which is down 4. So if I'm going to take my original function, and now I'm going to shift this whole thing down 4. 1, 2, 3, 4. Right here is my new y-intercept. And there is my asymptote. Now, if I actually graph this, I could get these numbers. and looks something like that. Now, where is my shifts? How do the asymptotes and intercepts change compared to the original? Well, my y-intercept is now at 0, -3, and it was at 0, 1. And so this shifted down 4, just like our whole function did. Okay, our asymptote is now not at 1, but at -3. So different things happen here. It wasn't 4, right? But I technically did go down 4, right? Normally my asymptote is at 1. And so usually this is y equals 1. And so I am 4 down when I talk about negative. Okay? Lastly, end behavior. If I am going towards infinity, where are we headed towards? And you should have said positive infinity. As x is going to negative infinity, y is going to that asymptote, which is -3. Or sorry, -4, not 3. Right, because I'm heading towards this line. Okay? Alright, I want you to pause the video and do those two. Think about the transformations, right? And where do they go? Worst case, you can always graph them on your calculator. So go ahead, pause the video. Alright, let's see how you did. So this should have been shifted left 3. The y-intercept goes from 0, 1 to 0, 1, 25. Okay, and the asymptote on this one actually is going to stay the same. Okay, and behavior would be a little bit different as it's going to negative infinity, but that's it. Okay, this one we should have the 6. We are shifted up 6. And then this is an inside negative, so this is reflected over the y. Okay, so if this shifts, everything shifts up, meaning that the asymptote shifts up 6. So this would be y equals 6. The y-intercept shifts up 6. So it started at 1. So we got 1 plus 6, so that would be 0, 7. Okay, and those are the two things that it wants us to compare. Okay, all right, flip it over. Now we're going to get into modeling a little bit. Okay, so I'm going to talk through this one, and then I'm going to give you the formulas for this. Okay, so it says a population of the large city was about 4.6 mil in the year 2020, and it grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over that 4-year period? So we got to gather some information. We have the initial population was 4.6 million. I'm just going to write in parentheses 2020. And it grew at a rate of, so we have a rate of 1.3%. Okay, now let's think about this. If I look at my original equation, so here's my exponential equation. Okay, we're going to learn in a second that A is actually the initial. What did we start with? So that is going to be my 4.6. Okay, B is a rate. And so I want you to think about this. If I am growing, right, if our population is growing, not only do I have the 4.6 million, but now we're getting bigger. And so in order to grow, we got to be over 100%. Which means we're going to take 100% and add in our 1.3% to get 101.3%. Well, I want that as a rate, so B is our rate, so that as a decimal is 1.013. Okay, so I just moved over my decimal 2 places, and so now we can set up our function. We got 4.6 is the start. My new decimal is that raised to the x, and here's my answer. Okay, if I follow up that question with, if it continues to grow at the same rate, what will the population be in 2050? Okay, so we have our population equals our 4.6 times 1.13x. Okay, so since 2020, we want to know what would the population be when it will hit 2050. Well, x, which is in years, would be 30. So it's not any more work, it's just inputting a number into the equation. So our total population is going to equal 4.6 times 1.013 raised to the 30. Okay, remember we're in millions of people first. So go ahead, type that in. And you should get about 6.78 million people. Okay, so we can use it for a setup. Now I want you to talk about our other vocab words. So we have exponential growth and decay. Growth, right, we're getting bigger. Decay, we're getting smaller. So, given an initial amount and the rate of increase or decrease, the amount after t time periods can be given in the 2 following situations. Okay, so we have our growth. We have this 1 plus the rate. Now, what was that 1 plus? This is like that 100%. Okay. If I am declining, if I'm decaying, right, I'm less than 100%. And again, this 1 is the 100%. So the key to this is that R is a decimal. Okay. Now, the growth or decay factor is equal to B. Okay, so make sure you have that idea down. So this factor is going to be equal to B, meaning we're not going to see it. It's already going to have subtracted out, and so we have to be careful with it. Okay, so let's see what we got. Here's our function. It says it can be used to model the value of a car in thousands of years after it was purchased. Okay, so does this function represent a growth or decay, and why? Okay, go ahead. Someone say it. And that should be a decay. And why is it a decay? Because our b value is less than 1. So our b value, remember, is right next to the x. Okay, it says now what is the rate of decay for this function, and what does it mean? Okay, so rate of decay is how much is it actually going down by. Okay, so that is b equals to 1 minus the rate. If it was growth, it would just say plus. Well, what is b? B is 0.8. So 1 minus what? That's our r, is 0.8. And we should get 0.2 is our rate. And what does that 0.2 mean? That we have a rate of decay by 20%. So the value depreciates after or each year from purchase. Okay. All right, flip it over. Okay, now my follow-up question to this, so there's our equation. It says graph the function, and what does the y-intercept and asymptote represent, and when will the value of the car be about 5,000? Okay, so let's go ahead and graph this. Okay, so let's look at our table once so we can see kind of what our asymptote is heading towards. That 6.7 e to the -4th, that is like 0. Okay, so if I'm looking at this, this is headed towards 0. So our asymptote represents, right, 0, well, $0 when the car isn't worth anything, because you got no money left, right? But what does the y-intercept represent? That is our starting point, right? Our y-intercept is always our starting point or initial value. Meaning that, right, it started off at $24,000. Okay, now it says when. When we got time. So that's our t, or our x, I guess. Okay, so now I can go ahead and look in here and see when would it be about 5,000. Remember, these are in thousands. And so if I look at this, I get about 7 years. So you look at the table in the calculator. Remember, this is just 5.0. And then it's about 7 years since 2020. Okay. All right, I want you to pause the video and go ahead and do this one. Okay, welcome back. You should have gone increasing because B is above 1, right? How many hawks were released? That was 220. That is my A value. And in what year will the number of hawks reach 280? Looking at the table, this should have been 5 years after, and our year was 2023, so that's 5 plus 2023 gives us 5 years plus that. So in the year, oops, I don't know why I circled the whole thing, 2028 would be when it would reach 280. Okay. All right, last type of problem is going to be comparing two different values. Now, we don't have either equation, okay, but let me read it. It says, a museum purchased a painting and a sculpture in the same year. Their values are changing exponentially as shown. Which artwork's value is increasing more quickly? Okay, so quickly, we're talking about the rate. So which one has a higher rate compared to everything else? Now, this first one, right, we have it. So the sculpture value, there it is. And so we have our B is 1.075, right? And so if I look at that, well, what is that a rate of? We're trying to figure out which one's increasing more. So we know this is a growth rate, and that would be equal to 1 minus B, or minus our rate. Okay, so our growth rate is equal to 1 minus our R. And so we got 1.075 equals 1, growth is plus, sorry. And so if I just subtract 1, we have our rate of 0.075. So move it over 2 decimal places, and we get a 7.5% growth rate. Okay. Now, we don't have our equation here. We just have some points. So let's work on how would I get an equation, or how do I even get my rate, my value. Okay. And so we're going to just set up our equation. We got f of x equals a times b to the x. Remember, this is the initial. And here's our rate of growth or decay. And so we have our initial amount. Remember, that is the y-intercept. And so A is actually 40. And then I don't actually know my rate, but I do know that this is x and y. So we're going to plug these values into the equation. So I got y is right here, right? We got my x is going up in the exponent, and we have our a, and so we are trying to solve for b. So I got 64.4 equals 40b raised to the 5th. So I'm going to divide by 40. And now this is where I'm going to keep this all on my calculator. So I got 64.4 divided by 40. Now 1.61 isn't terrible to write, so I could, I guess, write it like this. And now we got b to the 5th. So how do I undo a 5th root? Or sorry, a 5th power is with a 5th root. So we're going to take this to the 5th power. Now, how do I do that on this one? I'm going to go 5. I'm going to find math, and I'm going to go down to number 5, which is the x square root button. Okay, so when I hit enter, it puts the little 5 where it needs to be. I'm going to type in 1.61, and I get 1.0999. Now, we're trying to find the rate. Remember, this b value we're talking about is actually 1 plus r equals my 1.0999. And so when we subtract 1, we get 9.99, which is about 10%. So that is a bigger growth rate than the 7.5. So the painting is increasing more value. Okay. All right. That concludes today's lesson. I'm going to give you the homework for our lesson. So we have T6 L1 homework is on page 291, and we have 9, 11, 12. We got 13 through 27 odd, 28, 30, and 31. All right, thank you.